Dry steam at 118.6 degrees Celsius is passed through a pipeline which is connected to a chamber where steam loses 100 kilojoules per kg of enthalpy. Consequently, the steam is passed through another chamber where the steam is heated by 500 kilojoules per kg. What is the condition of steam and the related parameters at the exit of each chamber? Assume that specific heat of water is 4.187 kilojoule kg Kelvin and that of superheated steam is 2.25 kilojoules per kg Kelvin. Okay, now here as you can see, only temperature of saturated steam is mentioned. There is no mention of pressure. It is just given that dry steam is at 118.6 degrees Celsius. So we can simply consider 118.6 degrees Celsius as our saturation temperature. 118.6, if 118.6 is our saturation temperature from steam table, pressure is 1.90 bar. Pressure is 1.90 bar. And the other, let's write the other given quantities. In chamber A, steam loses 100 kilojoules per kg. In chamber A, I'll write a minus here so that we can identify it has lost. And it gains 500 kilojoules per kg in chamber B. This is not required anymore. Yes. This is plus 500 kilojoules per kg in chamber B. Now we need to find the parameters of steam at end of both chambers. Okay, now let's start. As we have considered, saturation temperature is 118.6 degrees because it is given in the question that it's dry steam. We are currently here. And in the chamber A, we lose 100 kilojoules per kg. That means we go back. So we don't know how back we are going, but we'll fall in this area, or if it loses enough heat, will fall in this area. From steam table, HF is HF is 497.9 kilojoules per kg. HFG is 2206.1 kilojoules per kg. Hg is 2704.0 kilojoules per kg. Okay, this is HF. This is 118.6 degrees Celsius, and this is HFG. Okay, now first let us do the chamber A. It is given that we are losing 100 kilojoules per kg. Okay, let's now first calculate how much energy does the steam hold at 118.6 degrees Celsius. It's nothing but HF plus HFG. So it is at saturation temperature. So enthalpy at saturation temperature is nothing but Hg, which is equals to 2704.0 kilojoules per kg. And from this we are losing 100 kilojoules. So now we'll have wet steam. Because for it to become water, we'll have to lose 2206.1 kilojoules per kg, which is not happening. So enthalpy of wet steam is nothing but 2604 kilojoules per kg. Okay. Now from here, from the formula we discussed earlier, that is from enthalpy of wet steam, which is nothing but enthalpy of wet steam is HF plus X dot HFG, where X is dryness fraction. So we know that it's wet steam. We need to find the dryness fraction. We will have to just substitute it. 2604 equals, we know HF 497.9 plus X dot 2206 0.1. 2604 minus 497.2. That is 2106.1 is equals to x dot 2206.1. You have to divide this by 2206. Okay, as we can see, x is 0.954. This is the dryness fraction, and the steam is wet steam. That is at the end of chamber A. Now let's move on to chamber B. Okay, we know at the end of chamber A, the enthalpy is 2604.0 kilojoules per kg, and in chamber B, we are adding 500 kilojoules per kg extra. So that is 500 plus 500 kilojoules per kg. So as we can see, if we add 100, we are reaching the 2704.0. That is nothing but the enthalpy at saturation temperature, at which everything is completely dry. So if we are exceeding that, we are going to superheated region. That is equals to 3104 kilojoules per kg. As we can see, it's greater than Hg. That means it's superheated. So now we'll have to use the formula for enthalpy of superheated steam to find the temperature at the end, after it comes out of chamber B. So enthalpy of superheated steam is nothing but HF plus HFG plus specific heat into temperature difference, that is temperature at superheated temperature minus saturation temperature. As we can see now, 3104 is equals to HF plus HFG. This is nothing but Hg, which is 2704, plus this is 2.25, as we are specified superheated temperature. So superheated temperature is what we need to find, and saturation temperature is 118.6. Okay, now 3104 minus 2704, which is 400, is equals to 2.25 of T superheated minus 118.6 degrees Celsius. 400 divided by 2.25, 177.77 T superheated minus 118.6. So if we add 118.6 to this, that is temperature of superheated temperature is 296.37 degrees Celsius. Okay, now moving on to the next question. The restaurant daily uses 600 kg of 95% dry steam produced at a pressure of 3 bar. The boiler is fitted with an economizer which increases the feed water temperature to 94 degrees Celsius and is fired using wood and paddy husk in equal proportions. The gross calorific value of wood and paddy husk is 155 or 15,500 kilojoules per kg and 12,600 kilojoules per kg respectively. The boiler has been operating with an average efficiency of 78%. Calculate the daily composition of wood and paddy husk. Okay, now let's write the given data here. Mass is 600 kg. Steam is 95% dry, which means dryness fraction is 0.95. Pressure is 3 bar, and using an economizer, the feed water temperature is 94 degrees Celsius. So which means the feed water temperature is 94 degrees Celsius. And gross calorific value of wood, GCF of wood, is 15,500 kilojoules per kg, and that of paddy husk is 12,600 kilojoules per kg respectively. The boiler okay, yeah, okay. Efficiency is 78%. Okay, now if pressure is 3 bar using steam table, HF HF is 561.5 kilojoules per kg. HFG is 2163.2 kilojoules per kg. Hg is 2724.7 kilojoules per kg. Okay, one more thing I forgot, that is saturation temperature at 3 bar. Let me look. 133.5 degrees Celsius. Okay, now let's draw the graph. This is Tsat, which is I think 133.5 degrees Celsius. And they give the feed water is at 94 degrees Celsius. Let us see it is here. And our final product, that is 0.95 dry fraction wet steam. Let us say it is here. The question is, if they are using same amount of wood and paddy husk, how much they are using. For that, first we need to find how much energy is required to produce 600 kilograms of steam. That is nothing but enthalpy of this area. This is HF. This is HFG. But we need this. For that, we have to subtract enthalpy of feed water from HF and then add just this amount to that. So let us say enthalpy after removing enthalpy. Let's first calculate enthalpy of feed water. It is nothing but 4.187 multiplied by 94 minus 0. That is 393.878 kilojoules per kg. We have to subtract this value from HF to get this portion. So if we subtract it, HF minus HFW, which is equals to 561.5 minus 393.578. 561.5 minus answer in 67.922 kilojoules per kg. And we have calculated this. We need to calculate this area. This not by area I mean this part of the energy. So that is, let us call that HFG. Let's call it HFG only. So that will be dryness fraction multiplied by HFG. I'm not adding HF here because we have calculated this energy which we'll be adding later. So we need just 95% of this. (2055.04 kilojoules per kg). Now the total enthalpy we need to raise water from here to here is 167.922, which is here, plus 2055.04, which is equals to 2222.96. 2222.962 kilojoules per kg. This is per kg, but we have 600 kgs, so we should multiply it with 600. Total enthalpy is multiplied by 600. Okay. Now this is the amount we need. Okay. Now we have the total amount we need. Now we have been given that efficiency is 78%. Okay. Now I would like to explain a little here. Efficiency actually means how much energy is being used divided by what amount of energy we are actually giving. So here we are using this much amount of energy. And so the amount of energy which is being given is when we burn wood and paddy husk. Let us say we are burning total X amount of fuel, but it is given that we are exactly burning equal quantities of both, which means we have X by 2 wood and X by 2 paddy husk. So what is the energy that is coming from this X by 2 kgs and X by 2 kgs? That is nothing but X by 2 multiplied by the gross calorific value, that is 15,500 plus X by 2 into 12,600. Okay, as we know, efficiency formula is Q into enthalpy difference. HS minus HF, as far as I remember, divided by the mass into calorific value. We can see here this is mass and this is calorific value. As we have two fuels here, we are separately multiplying them with the given mass. And this is nothing but this. So 78 divided by 100 equals. Now if we add 15,500 plus 12,600 and then divide them by 2. 1333777.2 x into 14050. Okay. X is 94.930. This multiplied by 100 divided by 78. 121.706. This is the total mass of fuel, but the separate mass of wood and paddy husk is this divided by 2, x by 2. So the mass is 60.853 kg of wood and 60.853 kg of paddy husk. Okay, for the next question, I don't actually have the question, but I have the values and I know the question. I'll explain it. So the values are, we have 2 kg of steam, so mass is 2 kg at a pressure of 0.048 megapascals. Okay, now 1 pascal is 10 power minus 5 bar. So 0.048 megapascals is, mega is 10 power minus 5 bar, which is equal to 0.48 bar. And the temperature is 150 degrees Celsius. Now, the actual question is, this 2 kgs of steam is being sent into 2 chambers, A and B, in the ratio 2:4. Now, in chamber A, steam loses 15% of its total heat. Also, after that, it loses 500 kilojoules. In chamber B, it loses 60% of its total heat energy. So we'll have to calculate the conditions and parameters of steam at the end of when it comes out of chamber A and chamber B. Okay, first let's draw the graph. Okay, before that you have to write HF and HFG from steam table. As we know, it is 0.48 bar. Okay, from here we can see T saturation temperature. It is 80.33 degrees Celsius. This is less than 100 degrees Celsius, which is less than our normal boiling point because we have atmospheric pressure which is less than 1 bar. And HF is 336.3 kilojoules per kg. HFG is 2308.0 kilojoules per kg. Hg is nothing but the sum, which is 2644.3 kilojoules per kg. Okay, now let us draw the graph. This is 80.33 and this is 150 degrees Celsius. This is HF, HFG, and this is enthalpy of superheated steam. Okay, before we do anything, let's find the total energy of the entire total energy of superheated steam. For that, from the formula, we know enthalpy of superheated steam is HF plus HFG plus specific heat at superheated temperature multiplied by superheated temperature minus saturation temperature. If we do this, we get HF plus HFG is nothing but Hg, 2644.3 kilojoules per kg plus superheated steam, so 2.25 multiplied by 150 minus 80.33. This will give us a total of 2644.3 plus 2.25 multiplied by 150 minus 80.33. 2801.0575 kilojoules per kg. Okay, now let's calculate the amount of mass that actually goes into chamber A and chamber B. So it is going in the ratio 2:4. So how much mass will actually go? 2 multiplied by 2:4 actually states that there are total of 6 parts, out of which 2 parts are going to chamber A and 4 parts are going to chamber B. So to find the total mass, we multiply 2 kgs with the fraction, that is 2 by 6. How much is going into chamber A divided by total? That is 4 by 6, which is nothing but 2 by 3 kg. Okay, let us leave it 2 by 3 kg. And into chamber B, it's nothing but 2 into 4 by 6, 8 by 6, which is 4 by 3 kg. If you have any doubt, if we add this both, 2 plus 4 divided by 3, 6 by 3, it is 2 kg. So the total mass is 2 kg. Okay, now we know how much mass has gone into which chamber. So if we know that, and if we know the energy per kilogram, we can actually find enthalpy in chamber A and enthalpy in chamber B. There's nothing. Enthalpy in chamber A is nothing but mass in chamber A multiplied by 2801.0575 kilojoules per kg. Same follows for B. This will give us 2801.0575 2801.0575 multiplied by 2 by 3. that is 1867.371 or 372 kilojoules. And if you multiply this with 2, it actually becomes 4 by 3, or else let's just do 4 by 3. That is 3734.743 kilojoules. Okay. Okay, now HB is 3734.743 kilojoules and HA is 1867.372 kilojoules. Okay, now let me draw a graph once again so that we don't get confused. Okay, now HA, we have 1867.372 kilojoules. From this, we are losing 15% of total heat. So that is nothing but 1867.372 minus 15% of total heat. 1867.372. That is nothing but 85 by 100 into 1867.372. That is 0.87, 0.85, 0.85 into 1867.372. 1587.2662. On top of it, we are losing 500 joules of energy. If I do kilojoules there, okay, this is a mistake. It's not 500 kilojoules, it's 500 joules. It was a mistake there. This is 0.5 kilojoules. Okay, now if you lose 0.5 kilojoules from this, it is nothing but 1586.7662 kilojoules. This is the energy left after all the processes in chamber A. Now let's come to chamber B. Here we are directly losing 60% of heat. That is minus 60% of total heat is lost. That is 0.4 multiplied by 3734.743. 3734.743 multiplied by 0.1493.8972 kilojoules. Okay, now as we can see, Hg, this entire thing which is Hg at 0.48 bar is 2644.3 kilojoules. Here we can see both of them are less than that, while HF is 336.3 kilojoules per kg. As we can see here, both of them are kilojoules and kilojoules, but we have HF and Hg in kilojoules per kg. So we have to divide this by the mass. So HA divided by the kg is 2 by 3 kg. So that gives us divided by 2 by 3. 2380.149 kilojoules per kg. Same with this, HB divided by 4 by 3, that is 1493.8972. 8972 divided by 4 by 3. 1120.4229. You can see in both the cases they are greater than HF, but less than Hg, which states us that they are somewhere here. So we need to find the dryness fraction of both of them. So 2380.149 equals 336.3 plus dryness fraction multiplied by HFG, which is HFG is 2308.0. Now if we calculate this, 2380.149 minus 336.3 divided by 23808, that is 0.885, 88.5% dry steam. Now here, if we do the calculation here, 1120.4229 equals 336.3 plus x into 2308.0. Again, 1120.4229 minus 336.3 divided by 2308.0. X equals 33.974, which is 33.974% dry steam. Thank you.